This video will look at how to do chi-squared goodness of fit using your TI-83, 84 calculator, your TI-89, and inside of GeoGebra. So suppose I have this problem where I'm looking at several comic books and I'm told that 80% of comic books have a regular style cover, 15% have an uncommon variant, and 5% have a rare variant cover. I collect a random box of 200 comics from this company, and I observe 170 of the first type, the regular, 20 of the uncommon, and 10 of the rare. What chi-squared goodness of fit does is it compares what we saw to what we were expecting to get for that distribution. Now, I have to type in both the observed and the expected into my calculator, so I have to do a little bit of pre-work this time around before I can just type things in. The expected is equal to the number of trials times the probability. So for example, if I want the expected number of regular comics, this is out of 200 comics. I was told that 80% should be regular. And if I do 200 times 80, I should have expected to get 160. So I can already see I'm off by 10 for that category. Next one, the uncommons. I have 200 is my number of comics total still. I was told this should be 15%. Multiplying this together gives me 30. I was expecting 30 uncommon. I actually got 20. Now, your total numbers here should add up to 200. Right now I'm at 190, so this last one should be 10. But just a quick check, expected for the rares, I have 200 times that 5% probability for rare is going to give me 10. Now to do this using my calculator, it is a two-step process. I'm going to type all of the observed values in list 1, and I'm going to type all of the expected values in list 2. I'm going to start with the TI-89 here. And I'm going to go to the same spot I always go when I'm doing statistics. I'm going to go inside of StatList Editor. So I'm going Apps, StatList Editor, and inside of list 1, I am typing in my observed values. So I have the 170, 20, and 10. In list 2, and to type things inside of a list, I'm just inside a list, I type in the number, and then I hit enter, and then I just keep going. So 160, 30, and 10. I now have my data typed in LIST1 and LIST2. The TI-89 is alpha sensitive, so when the time comes to say where the list is, if I just say L1, it won't know what I'm talking about. It has to be spelled out. I'm doing a test, so I'm going to choose F6, blue F6. And I'm choosing the option CHI2, this is chi-squared, Goth, that stands for goodness of fit. It'll ask me where the observed list is. Well, I don't want to have to type out all of that LIST2 business, so just a note, your calculator has this button down here that gives me the variable link, and I can pull up an entire list of value if I go inside of this option. I'm noticing that this writing is in blue, so I'm going to hit second and the minus button to pull up the list of all of my list. My X values, my observed values are in list 1. My expected values, I'm doing second, and then the minus, I'm going back into that var link. They were in list 2. And finally, it asked me about degree of freedom. Degree of freedom is the number of categories minus 1. In this last problem, I had 3 different types of covers, regular, uncommon, and rare. So my degree of freedom is going to be 2. I'm choosing calculate. I hit enter. It's going to give me my chi-squared value of 3.96. It's going to give me my p-value of 0.138 or so. So I end up with a reasonably large p-value when I ended up doing this test here, which means I do not have evidence that the distribution is different than claimed. In other words, my observed is close to my expected. If I have a really small p-value, that's telling me that these values are drastically different and that the distribution is not a good fit. Large p-value, good fit. Small p-value, not a good fit. Let's do the same thing now in a TI-84 calculator. And again, I'm going to need this observed and expected, so I'm just going to pull this to the side when I'm doing the TI-84. Stat. I'm doing a test, so I'm going over to test. And I'm scrolling, and I'm going to scroll down until I see chi-squared goodness of fit Goff test. I need my observed values in list 1 and my expected in list 2. So let's type in that data. Let's go back to stat, and let's choose the option for edit. So stat edit allows me to change values in a list. First list, I'm typing in my observed values, 170, 20, and 10. Second list, I'm typing in my expected, 160, 30, and 10. Going back to stat, going back to test, and I'm choosing chi-squared goodness of fit. I can now verify that I did actually type in my observed in L1 and my expected in list 2. My degrees of freedom is the number of categories minus 1. So 3 categories minus 1 is 2. The reason why that's 2, by the by, is I knew when I had just these 2 categories what that last value should have been. So I solved for this value 10, knowing the first 2. Degree of freedom is the number of categories that you need to know using some sort of multiplication trick in order to know everything. I'm choosing calculate. Same chi-squared, same p-value. This is looking pretty good. I'm going to show you this in GeoGebra as well. Inside of GeoGebra, I'm going into probability. I'm going into statistics. And I'm choosing the option for goodness of fit test. It gives me a spot for the observed. So I had 170, and then my next is my expected, so 170 and 160. I had 20 and 30, and I had 10 and 10. After I type in the values, it will automatically calculate my degree of freedom for me. My degree of freedom here is 2. My chi-squared is 3.9583, and my p-value is 0.1382. If you had more than 3 categories in your list, where it says row, you could pick how many categories you wanted to compare. That's how you do chi-squared goodness of fit using your calculator in GeoGebra. If it was a test for homogeneity or a test for independence, instead of using a list, we'd actually use a matrix of values. I will show you how to do that using your calculator as well.